Hey everybody, Dr. Powers here. I'm going to go through some problems that are going to be similar examples to the challenge activities for Module 5. This module introduces the idea of a hypothesis test. And so the hypothesis test is a fundamental kind of concept to statistics and really all of science. And then it's important to remember the main really philosophical idea of a hypothesis test. You have a null hypothesis, which is kind of your going assumption. What do you assume to be true going into this exercise? And then you have an alternative hypothesis, which is something that you're considering in opposition to your null hypothesis. You collect data, and you want to see if the data supports the alternative hypothesis, and if it supports it enough, you want to reject the null hypothesis. Basically saying that the null hypothesis, it would be it isn't consistent with the data that you have, right? That's really the idea. Now, it's not that we are trying to prove the null. If we end up not in the end, you say, we either reject the null hypothesis or we don't reject the null hypothesis. And this is an important concept. Some people want to focus on it more than others, but I like to make a point about this. In the end, the data that we've collected really represents evidence in support of the alternative hypothesis. We're not collecting evidence in support of the null hypothesis. We are not proving the null hypothesis true or false. We never prove anything true or false in statistics. It's all about managing uncertainty. We can reject the null hypothesis if we are fairly certain we're fairly certain it's inconsistent with the data. We can say that we have very strong evidence in favor of the alternative, so we reject the null. Doesn't mean that we've proven the alternative either. We just have very strong evidence in favor of the alternative. That's the way science works. Math is nice because we have certainty in math, but when we're working with real data, we can get a very, very good theory or a model, something like that. And we hold that model up as our null hypothesis, and we compare it to other hypotheses that might come around, and we see if the data supports these alternatives, and if it doesn't, then we retain the null hypothesis. It's the best that we have so far. All right, enough of that. Let's talk about these three scenarios and kind of outline what the null and the alternative hypotheses would be. The first one, a biologist claims that the average lifespan of a housefly is 10 days. So in all of these cases, we have the null and the alternative. Now, the null hypothesis is denoted H with a subscript 0. Let's put this in. The alternative hypothesis is denoted either H with a subscript 1 or H with a subscript A. There's really no consistency across statistics texts, and they're both equally used. Even capital A and lowercase a, there's no consensus. So I'll use H0 and H1. Here, the null hypothesis is that the average lifespan. Okay, so we're talking about averages here, and so averages, we're talking about mean, the population mean. So the null hypothesis is a statement about the population mean. And so if there's two hypotheses and one of them is a hypothesis that involves equality, for example, the hypothesis that the mean lifespan is exactly 10 days, that's going to have to be in the null hypothesis. The alternative in this case, since there's no sort of, this null hypothesis would be false if either the mean was greater than or less than. We're going to use a two-tailed alternative, which is going to look like this. The mean is not equal to 10. All right, that's how we would encode this. Let's take a look at the next one. A pollster claims a pollster claims the majority of voters support some candidate. A majority is more than half. Okay, so now we're talking about the proportion of voters, and we use the symbol P for proportion, for population proportion. Although in some cases, some books might use the Greek letter pi. I'm not going to, although I kind of like that idea. P equals 0.5. In some cases, you might see greater than or equal to 0.5, and you could argue that the second one is better, and I wouldn't disagree. The important thing is your null hypothesis has equality in it. Really, if the proportion is greater than or equal to 0.5, that's equivalent mathematically. So, and you'll see why when we start doing these tests. Anyway, the alternative would be that the majority of voters does not, which is clearly going to be P is less than 0.5. That's going to be the alternative. So remember, we had to have the claim that has equality in it be the null hypothesis. That's just the way that we have to do these hypotheses tests. Engineer believes that concrete on average is at least 2 million. Sorry, so an engineer believes that concrete on average is at least 2,400 kilograms, the density, in density. That's the average density. So we're talking here about the average density. So we're going to use the Greek letter mu for the mean. Here I'm going to use at least. You know what I'm going to do is I'm going to use the greater than or equal to for this. Mu greater than or equal to 2,400, and the alternative would be that the mean is less than 2,400. So that's the way we can encode these things as null and alternative hypotheses. There are, in most cases, in a lot of cases, the claim that's being kind of considered is what you would put in the alternative. But if the claim is, but really, the distinguishing factor should be like in which side of the claim does not have equality in it. I hope that's not too unclear. We'll see as we go through these things the difference. Okay, let's move on. A company makes batteries and claims the average lifespan of the batteries is 52 months. They sample 67 batteries. They find an average lifespan is 50.23 months. What are the hypotheses? So in this case, the null hypothesis, in this case, the mean is 52, and the null hypothesis and the alternative would be that it's not equal to 52. You could argue that the alternative hypothesis would be that the mean is less than 52, because their claim that they have a 52 average would be true if the batteries last at least 52 months, right, on average. But if they last less than 52 months on average, then they're kind of not meeting their threshold. I would kind of it's a little bit ambiguous in the wording, so I would tend to look towards this one. Just conceptually, it seems to be like the kind of thing that they would be more concerned with, right? The battery company wouldn't really care if their average was more than 52, but they would be concerned if their average was less than 52. So that's what they need to be safeguarding against. What's the test statistic? The test statistic is the sample average. The population parameter is the population average. It's unknown. That's the key thing here. The population parameter, the population average, isn't known. We can't say the population average is 50.23 or 52 or anything. That's the whole point of statistical inference. We don't know what the true population average is. We just don't know. We could have a hypothesis about it, but we could test some data, but unless we do a full census, we're never going to know for sure. All right, let's take another look at another one. A professor observed that the average grade on the final exam is 83.2. He thinks this is significantly higher than the expected average of 77. The hypotheses for this scenario I'm going to give you. The null hypothesis is that the average exam score for like this class and for all the final exams this guy teaches is 77. The alternative is that the average is actually higher. It's higher than 77, which would be, potentially, there might be evidence for that. Of course, this class's grades are treated like a sample out of all the final exams that this guy could give. Is this significantly higher, or could this have happened just by chance? That's really what the statistical test is all about. The test statistic is the average sample average of 83.2. Population parameter, of course, is the population average test score, unknown. We don't know what the true population average is. That's, again, the whole point of statistical inference. Here we have some data. The pumpkins at a farm have great variation of weights. A farmer claims the average weight of the pumpkins is 15 pounds. A sample of 32 pumpkins are measured, and the following pumpkin weights are observed. Okay, here are the weights in pounds. Do the data satisfy requirements to use the t-distribution? Well, a couple things to look at. First, we want to know how many there are. N, let's just count. N equals, what's the count? N equals, I'm going to use the count function just to count the numbers, although that's silly because it's told above. N equals 32. And so that's large enough probably. And let's take a look at a histogram just to see if there's approximately a bell curve-ish. Let's insert a histogram and just see. Oh, take a look at that histogram. Yeah, this is and the sample shape is bell curvy. So yes, generally, as long as the population is, looks kind of like a normal curve. It's not too skewed, fairly symmetric, a mode in the middle, that kind of a thing. And as long as the sample size is large, then the central limit theorem should pick up the slack, and the t distribution should be fine for doing this test. What are the null and alternative hypotheses? So let's state these here. So the null hypothesis is that the mean weight, mu, equals 15. The alternative is that the mean weight is not 15, so mu does not equal 15. That's how we would set this up, because in the wording up above, the pumpkins, the farmer claims the average is 15. He would be wrong if the average weight was greater than 15 or if it was less than 15, and so that's the alternative we're working with. We're going to calculate a t-statistic and its p-value. So first we need the, what I'm going to do is actually, I'm going to show you how to do this using the tools in Excel. What I'm going to do is create a column of 15s. Let's see if this is. I'm going to take the 15s and bring them down, and I'm going to go up to the data menu and up to the data analysis. And this is a data analysis tool pack which you might have to turn on if you don't have it on already. There are other videos online that tell you how to do that. I don't want to do that right now. I don't want to get into that. So at the bottom of the list, you'll see t-test, to sample assuming unequal variances. So I'm going to click OK. This is going to allow me to do the t-test using Excel. Excel's going to do all the heavy lifting. I'm going to click OK. The variable 1 range is going to be in these cells. Okay, A4 down to A35. Variable B range is from B4 to B35, and the hypothesized mean difference is 0. So, in other words, I'm looking at the mean being exactly equal to 15. Okay, now the output range, I'm going to select this cell right here for my, actually I'll put it right there, D17. Click OK and see what I get. Here's a t-test of 2 sample assuming unequal variances. this is the way of it's weird that it's a two-sample t-test, assuming unequal variances, because really there's just one sample. What we're doing is we're comparing a sample of just 15s with a sample of the pumpkins that we observe. Really, that's the main thing that we can look at going down is, you can see this tells us the sample mean here was 14.06. Okay, that was the sample mean from these pumpkins. Oops. And and then down below we have a t-statistic and a two-tail p-value. These are the two things we want. So here t is going to be negative 2.83826. The p-value is going to be 0.007932. The p-value tells you, kind of how plausible is the null hypothesis in light of the data. That's kind of what it tells you. It's actually a little more complicated than that. It really is telling you, if the null hypothesis were true, what's the likelihood of getting a sample that's kind of like this, right? So if the true mean of pumpkins weights is 15 pounds, what are the chances that we could sample 32 pumpkins and get a sample mean and sample data that's kind of looks like this or even more extremely different than what you'd get from just like a bunch of 15s? And so you got 0.007932. That p-value means that it's pretty unlikely. Under the null hypothesis, what we have observed is fairly unlikely. That would happen less than 1 out of 100 times, just by chance. And yes, so there is evidence. There is strong evidence to refute the farmer's claim. Short little rhyme: if the p is low, the null must go. So we reject the null hypothesis if the p-value is really low. Turns out that the mean weight of the pumpkins is we could say the mean weight is significantly lower than 15 pounds. And when we say significant, we're talking about statistical significance. It means it was distinguishable through a statistical test and is attributable not to just sampling variation and like sampling error, but actually to a true difference. Like there's strong evidence that there's really a truly the mean weight is is not 15. In fact, lower than 15. Let's keep going on. Okay, a microwave popcorn brand claims that on average there should be fewer than 15 unpopped kernels when popping stops. A sample of 15 bags is taken and popped. The number of unpopped kernels is observed below. Okay, so here's some data. It's a pretty small sample. From the histogram, can normality be assumed? Let's create a histogram. Insert statistical charts, histogram. I'm just going to look at that. Now here you see our histogram. It is, I'm going to say, yes, it's at least, this is pretty small number of bins. I'm going to edit the axis, right click on it, format axis. I'm going to put in 5 bins just to see how things look with a few more bins. I'm not super thrilled with that. I wouldn't say not really. I don't know. This doesn't look like a normal distribution. I would say, but for the sake of argument, we'll continue the t-test. Okay. So later in like a more advanced statistics class, you'd say, okay, well, if you fail the normality assumption with a sample size of 15 bags, right? Sample size of 15 is pretty low when the data does not have a normal kind of curve to it like this does. There are other kinds of tests you could do when the assumptions needed for the central limit theorem fail. We're not going to cover those here. So I'm just going to still just kind of proceed as if there is no problem. Okay, let's state the null and alternative hypotheses. So this is they claim that there should be fewer than 15. So what I'm going to use is, for the null, I'm going to say that the mean is greater than or equal to 15, and the alternative is that it's fewer than 15. Is really their claim is going in the alternative hypothesis. Is there enough evidence from the popped kernels that fewer than 15 on average, right? So let's get all these statistics. The sample mean. Use the average function to do this. Average of all of these numbers. Average those numbers. That's the sample average. The sample standard deviation. stdev.s. Okay, so I'm going to go and select all of these. And my n, well, I already know that's 15. But if you don't know that for sure, you can use the count function. Count it all up. 15 of them. Okay. The t statistic is calculated as such. You take the sample mean, 14.133333, minus the hypothesized mean, 15. I divide it by, in parentheses, the standard deviation over the square root of the sample size. That denominator is called standard error of the mean. I'm going to hit enter. I get a t statistic of negative 0.77336. The p-value is found since I'm doing my alternative hypothesis is that mu is less than 15. I'm going to use a lower tail t probability. So t dot dist, the left tail, because it's a left-tailed test, mu less than 15. I'm going to find the probability less than this t statistic. The degrees of freedom is 15 minus 1, and cumulative you always say true. We always want cumulative probability. Hit, and then I enter 0.226. What conclusion should be reached? That the p-value is greater than 0.05, our, like, let's say typical significance level. We don't have sufficient evidence to support the claim that the mean number of unpopped kernels is less than 15. Maybe more data would show this. Although, so if the true mean number of unpopped kernels is 15, what this is saying is that, you know, about 1 out of every 5 samples of 15 could look something like this. Although our sample mean is lower than 15, it's not low enough with a small enough, standard deviation that we would consider this to be, convincing. All right. Here we go. It's common knowledge that when men reach the age of 50 on average, they experience a midlife crisis. A car dealer decides to test this. She records the age of 50 men who purchase red sports cars. Can normality be assumed from the histogram? Okay, well, let's take a look at the first thing. I'm going to insert a histogram. This one looks good. I would say that definitely we have a normality assumption met. I would say yes. Let's do the hypothesis test. The hypothesis, the null, is that the mean, I'm going to just write it out in words here. The mean is equal to 50. The alternative, it's common when men reach the age of 50 on average, so that it's 50 on average. The mean is not equals to 50. That doesn't look very good, does it? Not equal to 50. All right. I'm going to go ahead and do the same kind of thing. I want to get X bar. Actually, let's go ahead and do the long way. Standard deviation, sample size, t, p-value. X bar is the average. Okay, 45.4. Standard deviation, stdev.s. 5.53. Okay, the sample size How many have been observed? 50 individuals, sample size of 50, and we're talking about the age of 50, just a coincidence. The t-statistic, again, this is going to be the x bar minus 50, because the 50 is the hypothesized mean, divided by, in parentheses, the standard deviation over the square root of the sample size. That's my t-statistic. That's extremely extreme. So the p-value is going to be, what you do is you, I'm going to take the t dot dist dot 2t, a two-tailed, because this is a two-tailed test. I'm going to find the two-tailed probability, but I'm going to put in the absolute value of my t-statistic. And I am going to put in my degrees of freedom of 50 minus 1. I know already this is going to be basically 0. Yeah. If you don't know what that e negative 0.7 means, that's you move the decimal point 7 places to the left. So this is 0.0000003. That's very, 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 very low. It is basically 0. It would be almost impossible for the true mean to be equal to 50, and a sample this size gives a sample mean so low. There is strong evidence that the true mean age of life of midlife crises is 50. Is not 50. Actually, it's just the mean age of a red sports car buyer. I don't want to it's just a joke. I mean, we haven't really said anything about midlife crisis. We're just saying there's evidence that the average age of purchasers of red sports cars is not 50. Okay. So we've done a bunch of hypothesis tests. Hopefully this has been helpful for you, and I hope that you do well on this module. I'll see you around. Bye.